Hello everyone. Today I'm going to present our work titled Toward Cost-Effective Adaptive Random Testing, an Approximate Nearest Neighbor Approach, published in IEEE Transactions on Software Engineering. My name is Cui-Chen Hui from the School of Computer Science and Engineering, Macau University of Science and Technology, Macau, China, and I am representing the research team led by Associate Professor Huang Rubing. My presentation can be structured into the following 6 parts. The first part is background and research gap, where we'll dive into why adaptive random testing matters, its limitations, and the specific problem our work aims to solve. Then, we'll move to core idea and basic principle, which introduces the key insight of using locality-sensitive hashing LSH for approximate nearest neighbor search to transform ART's efficiency. Next is LSH-ART, framework and implementations, where I'll walk you through the framework of our method. After that, we have experimental setup we use to evaluate our method. Following that, key results will present the empirical findings across effectiveness, efficiency, and cost-effectiveness. Finally, we'll wrap up with conclusions, summarizing our contributions. Now, let's begin with the first part, background and research gap. As we all know, software testing is a cornerstone of quality assurance, and random testing RT is a widely used technique thanks to its simplicity, easy implementation, and ability to quantify software reliability. It's applied in diverse scenarios. However, random testing has a critical flaw. That is, RT lacks test case diversity, leading to low fault detection effectiveness. That's because RT doesn't use any information from those test cases which have already executed. The researchers even described it as the least effective testing approach. To fix this, adaptive random testing ART was proposed. ART enhances RT by spreading test cases more evenly across the input domain, leveraging the observation that failure-causing inputs tend to cluster into failure regions. 2 mainstream ART variants are fixed-size candidates at ART FSCS and restricted random testing RRT, both of which outperform RT in metrics like F-measure, which denotes the test cases needed to detect the first failure. But here's the problem. Existing ART methods face high computational costs. Generating each new test case requires calculating the distance between every candidate and all previously executed test cases. Our goal is to design an ART method that retains strong fault detection effectiveness while drastically cutting down computational costs. To get there, let's take a closer look at how ART works. A massive chunk of its computation goes into calculating the distance between every candidate test case and all previously executed ones. In essence, this is a nearest neighbor search process. Specifically, identifying the closest test case to a candidate from the entire pool of executed cases. This is the main line that drives our research. How do we achieve this? Our key insight is to replace the exact nearest neighbor search in traditional ART with approximate nearest neighbor search. Specifically, we use locality-sensitive hashing LSH, a well-known approximate nearest neighbor technique, to efficiently find approximate nearest neighbors for test case candidates, instead of exact ones. Why we choose locality-sensitive hashing? It maps data points into hash buckets such that close points have a high probability of colliding in the same bucket, while distant points rarely do. For ART, this means we don't need to compare candidates with all executed test cases. Only those in the same hash bucket should be compared, like shown in this figure. We use the hashing function to map every executed and candidate test cases into different hash bucket. For the candidate, the red star only need to calculate distances with those executed test cases within the same bucket. This cuts down computation time. It should be noted that this approach is an approximate nearest neighbor search process. But ART's test case set is dynamic. The number of executed test cases grows with the testing process. So we use scalable SLs instead of the static one. Scalable LSH adjusts the hash bucket width dynamically and uses a hierarchical index. When an ordinary bucket is full, it upgrades to a super bucket, and its elements are rehashed into lower-level buckets. This ensures scalable LSH adapts to ART's changing test set. Now, let's dive into the LSH-ART framework. It has 5 core modules that work in sequence. First, construct random candidates. We generate a set of random candidates from the input domain fixed size. K equals 210 for FSCS, dynamic for RRT. Second, search for hash buckets. For each candidate, we traverse the index tree to find an ordinary bucket, not a super bucket that it belongs to. Third, identify approximate neighbors within this bucket. We calculate the candidate's distance to all test cases in the bucket and select the closest one as the approximate neighbor. Fifth, insert new test case. We add the new test case to its bucket. If the bucket exceeds capacity, we set the parameter equals 260. It becomes a super bucket, and all elements are rehashed. This framework ensures we retain all executed test case information, while only comparing candidates to a small subset of test cases. Compared with other ART approaches, our method achieved less time and space complexities. To evaluate our method, we designed experiments to answer 3 research questions. 1. How effective is LSH-ART at detecting faults? 2. How efficient is it at generating test cases? 3. How cost-effective is it at revealing software failures, balancing effectiveness and efficiency? Our experiments included 2 parts: simulations with 3 failure patterns: block, strip, point, 6 dimensions, 7 failure rates; empirical studies with 23 real-world programs and 3 configurable systems for non-numerical domains. Let's move on to our results. For effectiveness evaluations, compared with RT, our approach also has favorable conditions according to the F measure, block and strip patterns with low dimensions. Compared with the ART variants, our approach has comparable F measure results overall, and sometimes slightly better performance, especially in high dimensions. Overall, our approach has better P measure results than RF and CR, and comparable results to DF and KD. As for the efficiency and cost-effective evaluations, first of all, our approach can generate test cases with same set sizes within less time compared with other ART approaches in high dimensions. And our approach is less cost-effective than RT for nearly all programs, is much more cost-effective than the original ART for all programs, and our approach is more cost-effective than DF in all the scenarios, and has better cost-effectiveness than RF, CR, and KD in most scenarios. Here we list the main contributions of our work. 1. We have proposed a new ART approach that uses locality-sensitive hashing, LSH-based ART. 2. We propose a framework to support our approach and present to implementations, FSCS version and RRT version. 3. Our approach maintains comparable testing effectiveness, including fault detection effectiveness, to the original ART and its variants, sometimes obtaining better results, especially for high dimensions. 4. Our approach has better testing efficiency, generally incurring lower computational costs than the original ART and its variants, especially when the input domain dimensionality is high. 5. Our approach is much more cost-effective than the original ART in all scenarios and outperforms the variants in most scenarios. That's all about my presentation. Thank you for your attention.